Welcome to Model Evaluation and Performance Metrics, part of the Fundamentals of Machine Learning course aimed at training AI practitioners. In this lesson, we'll explore how to assess whether your model is performing effectively or if it's merely memorizing data. You'll learn about core metrics like accuracy, precision, recall, and the F1 score, and why these measurements matter. We'll also discuss methods like cross-validation to ensure your model is robust and discover strategies to avoid overfitting. By the end, you'll have a solid framework for evaluating any ML model. Imagine building a house without testing its structural integrity. It might collapse unexpectedly. Likewise, a machine learning model needs rigorous evaluation to ensure reliability. Without proper metrics, you risk deploying a model that looks good on the surface but fails in real-world use. Evaluation catches overfitting, when your model memorizes training data, or underfitting, when it fails to learn enough. Think of it as a report card revealing how well your model adapts to different scenarios. Accuracy is the simplest metric, the proportion of correct predictions out of all predictions. For example, if your model classifies 80 emails correctly out of 100, it has 80% accuracy. This is fine if classes are balanced but can be misleading for rare events. A model labeling all transactions not fraud might get high accuracy, yet ignore actual fraud cases. Accuracy alone doesn't always reveal a model's true performance when dealing with skewed data. When class imbalance is significant, precision and recall become vital. Precision measures, out of all predicted positives, how many are correct. Recall measures, out of all actual positives, how many you caught. In spam detection, high precision avoids mislabeling genuine emails as spam, while high recall catches more spam but risks false alarms. Each task dictates which metric matters more. Are we minimizing false positives or false negatives? Understanding both metrics helps tailor your model's trade-offs to real needs. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. A high F1 score indicates your model isn't just good at precision or recall, but maintains a strong equilibrium between them. This is especially handy for imbalanced data sets where accuracy can mislead. However, context still matters. If missing a positive case has huge consequences, you might sacrifice some precision for higher recall or vice versa. Choose F1 when both dimensions matter equally. Consider a hospital deploying an AI model to detect a critical disease. If the model prioritizes precision, it may reduce false alarms but miss true cases. Focusing on recall might catch more patients but trigger countless false alerts. Balancing these metrics is crucial in a high-stakes setting. Doctors usually want as many genuine cases identified as possible, high recall, without overwhelming staff with false positives. The right blend hinges on clinical context and resource availability. A powerful tool for visualizing predictions is the confusion matrix, a 2x2 grid showing true positives, true negatives, and false negatives. For spam detection, rows might represent actual spam/not spam, and columns predicted spam/not spam. By inspecting each cell, you see where the model makes mistakes. From this, you can derive accuracy, precision, and recall. A single accuracy score can hide which type of error is most common, but a confusion matrix gives a clearer picture of your model's strengths and weaknesses. Overfitting occurs when your model memorizes training data rather than learning general patterns. It scores perfectly in training, but fails on new, unseen data. Think of a student who memorizes practice test answers without truly grasping the material. Any unexpected question leads to mistakes. You detect overfitting by testing on separate data or using cross-validation. Regularization techniques, like L2, or stopping training early can also help. Remember, a fancy metric can't save you if you're only testing on the training set. Cross-validation is a method to maximize limited data and avoid deceptive results. You partition your dataset into folds and repeatedly train on some folds while validating on others. For instance, in a 5-fold setup, each fold acts as a test set once while the others form the training set. The average performance across all folds reflects how well your model generalizes. Think of it like rotating referees. No section of data remains untested. Cross-validation adds robustness to your metrics, helping ensure your model isn't just memorizing one slice of data. Picture an online retailer predicting who's likely to buy certain products. Initially, accuracy seems high because many users don't purchase, inflating the correct not-buy predictions. But by analyzing precision, recall, and the F1 score, the company notices it misses many potential buyers. They conduct cross-validation to see if these results hold across user groups, then fine-tune the model's hyperparameters. The improved F1 lifts revenue by recommending the right items to the right customers. Fewer missed opportunities, fewer bad recommendations. Fraud detection is another prime use case. A model with high precision but low recall might catch the most blatant fraud but miss subtle scams, resulting in big financial losses. Conversely, high recall flags many suspicious transactions, but might annoy genuine customers with false alarms. Striking a balance, or intentionally favoring recall, depends on the cost of missing a fraudulent case versus wrongly flagging an innocent transaction. Metrics like F1 help you find a middle ground, but domain knowledge ultimately shapes your choice. To deepen your understanding of model evaluation, sites like Kaggle and the UCI Machine Learning Repository offer datasets you can explore. Each competition or dataset often highlights different metrics. Some focus on accuracy, others on F1, or even AUC. Browsing these examples clarifies how metrics vary by project. You'll also find rich community discussions on code, approaches, and metric trade-offs. These real-world challenges help you see why picking the correct metric can make or break a model's success. Try different models like logistic regression or decision trees and compare metrics. A confusion matrix reveals where misclassifications occur, and cross-validation ensures your results aren't just luck. Note how tuning hyperparameters alters precision, recall, or F1. By systematically measuring these changes, you'll gain first-hand insight into how each tweak impacts real outcomes, preparing you for real-world deployments. In this lesson, you learn foundational metrics: accuracy, precision, recall, and F1, each revealing different aspects of a model's performance. You saw why avoiding overfitting and using cross-validation are crucial for honest evaluations. Practical scenarios, from spam detection to hospital diagnoses and product recommendations, show how the right metric depends on real-world goals. By carefully choosing and interpreting performance measures, you transform an untested model into a reliable tool. This knowledge is your roadmap for building models that genuinely excel in any environment. Selecting the right metric isn't just a technical detail. It shapes decisions, business strategies, and societal impacts. Accurate evaluation can mean safer medical diagnoses, more effective fraud detection, or better customer experiences. With cross-validation and well-chosen metrics, you can avoid illusions of success and create truly robust models. That translates into improved reliability and trust. Congratulations on completing this module. Continue using these metrics and best practices as you develop machine learning systems that have genuine positive impact.